We're still working toward how to use matrices to solve systems of linear equations. And before we get there, of course, we need to talk about what a matrix is and how we think about the different parts or components of a matrix. So here are 4 examples of matrices. We usually call a matrix by a capital letter. So we would say that this is matrix A, this is matrix B, matrix C, and matrix D. And you can see that we've used those capital letters A, B, C, and D to name these matrices. You want to think about a matrix as just an array of values. What it does is it allows us to express information in a simpler way than we otherwise would have been able to. For instance, matrix A might have represented the system 2x equals 6 and negative 1x equals 0. That could have been a system of 2 equations in one unknown, but instead of writing out 2x equals 6 and negative 1x equals 0, we can just simply write the matrix 2, 6, negative 1, 0 and have it represent the same thing. So matrices give us a way to arrange a lot of information in a simple way. And as you can imagine, when it comes to systems of linear equations especially, depending on what we're trying to do, we might have a situation where we have 100 equations in terms of 100 unknowns. Writing those out as a system of linear equations would be at the very least extremely tedious, if not almost impossible. But representing that system with a matrix is just about writing all of those coefficient and constant values in a matrix array like this. So that's how we want to think about a matrix, is just a simple arrangement of data. And when we talk about matrices, we want to be able to refer to particular values in between them. We also want to be able to know their dimensions. So let's go ahead and talk about the dimensions of each of these matrices before we talk about particular entries in each one. So as far as dimensions go, we always indicate dimensions as rows by columns. So we want to go ahead and say rows by columns. So for matrix A, there are 2 rows, the 2, 6 row and the negative 1, 0 row. So there are 2 rows, and there's 2 columns, the 2, negative 1 column and the 6, 0 column. So we write the dimensions of matrix A as 2 by 2. Matrix A is a 2 by 2 matrix. Matrix B, on the other hand, has 2 rows and 1, 2, 3, 4 columns. So matrix B is a 2 by 4 matrix. Matrix C has 3 rows and 1 column, so it's a 3 by 1 matrix. And matrix D has 1 row and 4 columns, so it's a 1 by 4 matrix. And keep in mind that a matrix can really have any dimensions that we want it to. It can be as small as a 1 by 1 matrix with just 1 row and 1 column, and that might look something like this if we said we had the matrix E is equal to, let's say, 3. That's a 1 by 1 matrix because it just has 1 row and 1 column. That's the smallest possible matrix, and a matrix can be infinitely large. We can make it as large as we want to. We can have as many rows as we want and as many columns as we want. You can have 1 column matrices like this one, 3 by 1, or 1 row matrices like D here, 1 by 4. You can have rectangular matrices. B, C, and D are all rectangular. They don't have an equal number of rows and columns, so we call them rectangular matrices. A is a square matrix. It's square because it has the same number of rows as it does columns. And so when the rows and columns are equal, we call that a square matrix. Now we also want to be able to identify particular entries in a matrix. We usually call those out using the matching lowercase letter as the uppercase name of the matrix. So here with matrix A, if we want to call out a particular entry, we use a lowercase a, and then we indicate the row and column. So this entry here, A12, is the entry in matrix A, capital matrix A, in the first row and second column. So if we look at the first row, 2, 6, and then the second column here, 6, 0, that is the entry 6. So A12 is 6. A21 is the entry in matrix A in the second row, first column. That's negative 1. And you can see here that this is pretty simple. So B22 is in the second row, second column. That's this 0 right here. B14 is going to be the first row, fourth column, which is 8. And B23 is going to be the second row, third column. That's the negative 1 right here. So you can see that the most important thing really is just remembering that it's always rows times columns so that you get the correct row and column and don't flip those and say columns times rows. So you want to think row and then column always for dimensions and for particular entries. So let's think about it the other way here. If I asked you which entry is the 1 in matrix C, well, we would say that that is in the first row, first column. So that's going to be C, lowercase c, 1, 1. The 2 is in the third row, first column. So that's going to be in C, 3, 1. And then what about these values here in matrix D? The 4 is going to be in the first row, of course, the only row, first row, second column. So that's going to be equal to D, first row, second column. The 0 is in the first row, third column. So first row, third column. And the 6 is in the first row, fourth column. So the entry in D14 is the 6 that we see right here.